I'm going to talk about holomorphic dynamics, okay? One-dimensional holomorphic dynamics, transcendental entire functions. So let me thank the organizers once more for this chance to be here. I really enjoyed, it was very inspiring to see so many talks which are on different topics, yet subtly related to what I usually work on. So I will talk about, let me thank Luna for the short introduction to this colorful world of transcendental dynamics. And I will actually start from one of the last slides of Luna. You remember when she was talking about periodic rays landing, repelling periodic points between landing point of rays? Well, I will essentially do the analog of this theorem, but for transcendental maps instead of polynomials. So I'm going to talk about entire transcendental functions, the dynamics, obviously, of entire transcendental functions, which act naturally on the complex plane C. What is an entire transcendental function? It's a function which is holomorphic on all of the complex plane, like a polynomial, but it has an essential singularity at infinity. And let me remind you that near the essential singularity, the function takes every value on the complex plane infinitely many times, with at most one exceptional value. So what are we? So there are two dynamical splitting of C. One is a splitting between the Fatou set, which is the set where the dynamics is stable. So in Luna's example of the circle is like the interior, the circle for Z squared. It's the interior of it's the unit disk and the complement of the closed unit disk, while the unit circle is the Julia set. And then another splitting that Luna kind of used, but not explicitly, is the splitting in terms of whether points escape to infinity or not. So when you have polynomials, you have a dichotomy. Every orbit either converges to infinity or stays bounded. So the set of escaping points are the set of points whose orbits converge to infinity. When you are in transcendental dynamics, everything is more complicated. You can have points which escape to infinity. You can have points whose orbits stay in a compact set. But you can also have points which go all the way to infinity. And then because you're near the essential singularity, you can come back and then go again. And I like to call them bouncing point, but it's not official terminology. So let us call them non-escaping points with unbounded orbits. And let me remind you what the Fatou set is, OK? So the Fatou set is the set where the dynamics is stable. In which sense? It means that if you take a neighborhood of a point in the Fatou set, then the iterates of the function form a normal family. What is a normal family? It's a family which is pre-compact. That is, for each sequence, you can find a convergent subsequence with respect to the topology of uniform convergence on compact sets. Said in other words, the Fatou set is the set where the points move together with all the neighborhood. So if you have a point which does something, all points in the neighborhood of it do the same, have the same behavior. So before getting into the problem that we are going to discuss today, let me give you some hints about what is special about holomorphic dynamics with respect to topological dynamics, for example. For example, the fact that your map is holomorphic tells you that you really have one dynamical direction. So your classification of fixed points, and hence periodic points, is very limited. You can have repelling points. These we are all familiar with. These are points for which a neighborhood is mapped outside itself, and for which the multiplier, that is the derivative, has modulus strictly bigger than 1. Then you can have attracting points, which again is something that everybody is familiar with. They are things. They are points for which a neighborhood is mapped strictly inside itself. And then you have indifferent points. So when the derivative has modulus 1, and you have something called the rotation number, this theta here, and there you have different situations. You can have parabolic points if the rotation number is rational, and in this case you have a certain number of attracting and repelling directions. I don't want to go into this. You can be a Siegel fixed point if your angle is irrational, but it has some nice arithmetic properties, so the germ is linearizable, the map is linearizable in the neighborhood. That's called the Siegel point. Or you can have Kramer fixed points, These are the points which are indifferent with a rational multiplier, but near which the dynamics is not linearizable. And you have very interesting structures arising near Kramer points, which are called hedgehogs, and which are non-locally connected continua. And there is much more to say about it. But for today, let me just point out that if you have repelling points, parabolic points, and Kramer points, these points belong to the Julia set, because the dynamics nearby is unstable in the sense that if you have a repelling point, everything is mapped out and eventually covers the plane. If you have a parabolic point, you have some directions in which the dynamics goes in, some directions in which the dynamics goes out. And if you have Kramer point, you have some complicated rotation. While, of course, attracting and Siegel points are in the Fatou set. So let me tell you a couple more words about the Fatou set and the Julia set. As we said, the Fatou set is the stable set, and it's very well understood in one complex dimension. When you study complex dynamics in one variable, the Fatou set, there is very little to understand left. Why? Because we have a complete classification of all the Fatou components that you can have for a transcendental entire function or a polynomial and even rational maps. And the other important thing that will be important for us today is that the Julia set is the closure of the set of repelling periodic points. So in a certain sense, understanding very well what happens to this set of repelling periodic points is helping us to understanding the dynamics on the Julia set, which is the thing that we need to understand most when we look at dynamics of holomorph maps in one dimension. And let me tell you one more thing. So essentially, our talk today will be dealing with the relationship between the Julia set, and in particular, the set of repelling periodic points, and the escaping set. So let me point out that for the class of functions, of entire functions that we will consider today, the escaping set will be in the Julia set. And let me go back again to polynomials. So you remember again in Luna's example, what happens? You have, when you consider polynomials, you have points which escape and points with bounded orbits. The points with escape are an attracting basin for infinity, which is a fixed point. So all the escaping points belong to the Fatou set in polynomial case. But because infinity is an essential singularity, it's no longer an attracting fixed point in our transcendental setting. In our case, at least for the class of maps that we will consider, escaping points are in the Julia set. So what is the topic that we will cover today? We will study the relation between the set of escaping points and the set of repelling periodic points. And in particular, we will try to understand, well, first of all, whether we can see that we can define something like rays in the transcendental setting. I'm giving you more details later. And we will try to understand whether some special rays, namely the periodic ones, have limits which are periodic points. This is what Luna showed in her last slide. And whether it is true that all repelling periodic points are accessible. And here, you remember the accessible points from Luis Hernandez's talk. So we will really try to understand whether every repelling periodic point is accessible by one of these curves of escaping points. And as Luna said, this is a very difficult question. You need a lot of understanding. You already need a lot of work in polynomial setting and related setting. This is what Luna did. And you need even more work in the transcendental setting. So the motivation is to deepen our understanding of the dynamics of these transcendental maps because as we said, the Julia set is the closure of the set of repelling periodic points, and the dynamics of the Fatou set is relatively well understood. And let me give you let me talk about what happens for polynomials, and then I will give you a little bit more motivation. So if you have a polynomial whose parameter belongs to the quadratic polynomial whose parameters belong to the connectedness locus, or equivalently such that the set of non-escaping points is connected, this is your set of non-escaping points. And the complement is the set of points whose orbits converge to infinity. And you can see that this is simply connected. So you have a Riemann map, phi. This is the definition of rays that Luna was using. I'm just going over it because I need something more about those rays than what Luna said. So this Riemann map has the very special property that it conjugates the dynamic of your map, your favorite one, z squared plus c, where c belongs to the connectedness locus, to the dynamics of a model map, which is z squared. And we know exactly what z squared does outside the unit disk. What does it do? If you take a straight ray of some angle theta, well, this is theta equals 0, but you can do it for any theta, then the straight ray of angle theta maps to the straight ray of angle 2 theta, because it's on the angle coordinate is just a doubling map. And on the Rayleigh coordinate, it will map points farther and farther closer to infinity. So when you push forward the straight rays to the dynamical plane of your true function, you will get a certain number of rays, or of curves, that you know very well how they behave when they come from infinity. But you don't know so well when they approach, you know. This is the Riemann map going from the complement of the disk to the complement of your set of non-escaping points. And there is this Carathéodory's theorem, which tells you that you can extend this map as a homeomorphism to the boundary if and only if the boundary of your target set is locally connected. So when these sets of non-escaping points, when these field Julia sets have boundary which is locally connected, all the rays that you can define on the dynamical plane, all the images of these curves under the Riemann map, converge nicely to some specific point on the boundary. But when these Julia sets are non-locally connected, the curves may start nice from infinity and then start accumulating in some weird way, possibly on the entire Julia set. So what is important for us is that what I find very interesting is that these rays put a symbolic dynamics on the set of escaping points. This the dynamics on the complement of this field Julia set splits into some radial direction in which you just move to infinity, and some angular direction on which you have the double angling map, the angle doubling map. And if you see what is like the archetype of dynamical system, one of the archetypes of dynamical system is the shift map on sequences. So a model is the shift map sigma, which maps a sequence A0, A1, A2, blah, 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 to the sequence A1, A2, and so on, where you forget the first digit. And if you write this angle in in binary expansion, then your map theta goes to 2 theta. It's exactly like saying that your angle written in whatever binary expansion it has goes to the sequence which is the image under the shift map. So you have introduced a symbolic dynamics on the set of escaping points. And when your Julia set is locally connected, this symbolic, so every ray converges to a point on the Julia set, and this point on the Julia set inherits the symbolic dynamics that you had on the ray. So you get a complete combinatorial description of points in the Julia set in terms of a model system, which is just a shift on sequences. For z squared, it's the shift over sequences over 2 symbols. For polynomials of degree d, it's the shift over sequences over d symbols. And guess what? For transcendental maps, it will be the dynamics of the shift on sequences with infinitely many symbols. One more little bit about motivation. So Olga yesterday was talking about the stable set. When you look at the family of quadratic polynomials z squared plus c, you also can define the set of parameters where the maps are, which are structurally stable, okay? But while in Olga's setting, you could know that if you are structurally stable, you are hyperbolic. This is a big open question even for quadratic polynomials. It's called rigidity, MLC, Mandelbrot local connectivity. It has many names because there are many, many related conjectures. But essentially, the point is it true that for quadratic polynomials, all structurally stable parameters are also hyperbolic? It is not known, but this theorem about landing of rays and repelling periodic points being accessible by periodic rays is related to this conjecture and helps you to understand some special cases. So there will be no more motivation. And let me go on to see what makes transcendental functions special. So what is a holomorphic map? A holomorphic map is essentially a covering outside the set of critical values. And so for polynomials, critical values are just images of critical points. While for transcendental maps, you also have another special type of value. Let us first think about what is a regular point for a covering. It's a point such that if you take a sufficiently small neighborhood, all its preimages, which will be infinitely many in the transcendental case, have one-to-one preimages. You take a small disk, all the preimages, the topological preimages of this disk are small disks which are mapped one-to-one. What happens when you take a critical value like z squared plus c? C is the image of the critical point, which is 0. What happens in this case? You have, no matter how small a neighborhood you take, you have many, many little disks which may be mapped one-to-one, but you have at least one disk which is mapped d to 1 with some degree d strictly bigger than 1. So this is a critical value. And if you have another special type of singular values which appears for transcendental functions, these are called asymptotic values. And what is this? It means that no matter how small you take a neighborhood, you always have one of the preimages of this simply connected neighborhood, which is an unbounded set. If you want, you can morally think about there being a critical point at infinity, which is mapping to your asymptotic value. So this is just to understand the fact that your function is really an unbranched covering if you outside the set of singular values. In what precise sense? That if you take away all preimages of the singular values and all singular values, then the function from C minus the preimages of the singular values to C minus the singular values is really an unbranched covering, infinite degree, because we are transcendental. So in a certain sense, the singular values are really what make the dynamics interesting. Otherwise, you would just have a covering. And, well, I wouldn't say nothing going on, but still the dynamics would be much simpler to understand. Yes?
What picture do you have in mind for S of F? Is it totally disconnected? Or?
It's not clear at all. It can be, it's not totally, so the critical values cannot accumulate, but the asymptotic values can accumulate. And you can find examples of transcendental entire function where the set is singular value is as non-empty interior, for example. It's very weird. So it's very counterintuitive at first sight. But you can have infinitely many, and they can accumulate in compact sets. They can even have non-empty interior. And it's very useful when you do dynamics to be able to take inverse branches, right? This is one of the reasons why people like to study homomorphism so much. So if you are outside the set of singular values, you can take one inverse branch. But if you want to take many inverse branches, and be sure that they are well-defined and univalent and so on, then you have to consider all the forward iterates of the singular values. The set of all forward iterates of the singular values is called the postsingular set. And the nice property is that if you are, so the postsingular set may be all of C, okay? In that case, you have no hope of taking a lot of inverse branches anywhere. But if your postsingular set is, for example, bounded, and you are outside the postsingular set, this means that you take a simply connected set. This means that you can take as many preimages as you want, and you know that the preimages are always well-defined and univalent. So our standing assumption for today is that the postsingular set will be bounded because we will really use this ability to take preimages in the complement of the postsingular set. And let me remark that the assumption that you are in the connectedness locus for polynomials is equivalent to say that the postcritical set is bounded for polynomials. So this assumption is really the analog of the assumption, is formally the same as the assumption that you need to put for polynomials in order to prove what Luna said, that periodic rays land and that repelling periodic points are landing point of rays. So what about the structure of the escaping set for transcendental maps? For polynomials, we have seen that it is an attracting basin of infinity. For transcendental map, the structure is much more complicated. But in many cases, namely when the set of singular values is bounded and you have some additional geometric assumptions that I don't want to get into, then you can show that the escaping set still consists of curves, and that these curves are endowed with symbolic dynamics, in the sense that the dynamics on this curve is conjugated to the dynamics of the shift map on sequences. So to each one of these curves, you can attach a label, which you can see as a sequence in Z to the n. And the dynamics, which maps one curve to the other, is semi-conjugate to the dynamics of the shift map, which maps its sequence to the shifted sequence. Yes? It's a set of escaping points. Sorry, I didn't stress this. So the set of escaping points, I will call it I of f for the rest of the talk. I have no idea why I, and not E. Maybe because E is exponential, I don't know. But traditionally, it's called I of f. It's a set of escaping points. Thank you. So what should you imagine these dynamic rays to be? You should just imagine them to be, like in the polynomial case, some curves which start nicely when you are near infinity, and then when you come in compact set, they may start accumulating, going back to infinity, and doing weird things. But, yes?
I'm stuck in the first sentence.
So let's take a function with bounded set of singular values.
No, the very first one, I of f consists of curves, like in the polynomial case. What does that mean?
So that the set of escaping points, so for each point in the escaping set, you can find a curve joining this point to infinity. So it consists of curve like in the polynomial case, in the sense that every escaping point is on a curve consisting of escaping points. But it's not like for polynomials where you can move holomorphically from one curve to the other because you have an open set. Here, between any two curves in the escaping set, you have points in between which do not escape. So it's really like a counter set structure times half a line. Does this make more sense? Maybe the like word is a bit confusing. They are pairwise disjoint, they don't self-intersect, you know very well what they do near infinity, and you have no clue what they do when they come in the compact set, and they are endowed with this symbolic dynamics that I think, okay, here's the pointer. This I'm just saying that they are endowed with symbolic dynamics. And there are two properties of these curves that we're interested in. Some of them are labeled by a periodic sequence, and we call them periodic rays. This means that since we have this semi-conjugacy with the shift map, this means that they come back to themselves after a certain number of steps. The other thing that is important is that we will be very interested, in the case in which these rays land. We say that a ray land if when you take the closure of the ray and you take away the ray itself, you just get a point. So for example, in this case, if you do some weird things, but then eventually you converge to a point, you land. But if you do some things like the sine curve, and you eventually accumulate on an entire interval, then you don't land. And it is known, so there are many examples of rays which don't land. But it's conjectured that periodic rays always land, no matter which assumptions you take, well, except there is singular values on the rays, and you can prove something in some cases. So what is the theorem? The theorem is that if you take a transcendental map for which rays exist, so you need this geometric condition. Important. You don't always have curves. There are counterexamples. If you drop the geometric conditions which ensure the existence of this curve in the escaping set, you can find an example of transcendental entire functions, which are hyperbolic even, for which the path-connected components are points. Of the set of escaping points are points. So you really need these geometric assumptions to have curves. But I will go back to this again. And so we need, so for this theorem, for this theorem and this talk, we will need the geometric assumption that rays exist, and we will assume that the postsingular set is bounded. And in this case, it was previously known that all the periodic rays land, and where can they land? They need to land at repelling or parabolic points, because Siegel points and attracting points are in the Fatou set, so they're not accessible from the set of escaping points. And Kremer points, there is something called the snail lemma, which ensures you that you can't land there. And we also, so this was kind of done. And you can also prove the converse of the analog of the Hubbard theorem, which tells you that all repelling and parabolic periodic points are accessible by one of these curves. And this is really new, and it is kind of the hardest part to generalize from the Hubbard landing theorem, because the Hubbard landing theorem, this part really uses the fact that you have a basin of attraction for infinity. So let me do two remarks. The first one is that the assumption that the post-singular set is bounded is formally the same as the assumption that you have for polynomials that you are in the connectedness locus. Formally the same. No, so this theorem is with Lasser and Pegillen, the big theorem. But for some special case, like for parabolic, it follows from a theorem which is apparently totally unrelated. Parabolic points? Yeah, for parabolic points, it follows from a theorem with Nuria Fajaya, which is surprising because it's unrelated, it's an unexpected corollary. And then this work for general transcendental entire function is originated by a work I did with Lyubich during my PhD thesis, where we proved the same theorem for the exponential maps. There are two special cases that were known before. For the exponential family. Yeah, for e to the z plus c. So when you don't know what to do in transcendental dynamics, when you have a big problem that you want to attack, you start with the exponential, usually. And so you do that first, and then the exponential is super nice, the geometry is super nice, you will see better later, and then you try to generalize. So as I said, the assumption that the post-singular set is bounded is formally the same as for polynomials, but it's substantially very different, because in polynomials, you either escape to infinity or you stay in a bounded set. While in the transcendental case, you may accumulate on the post-singular set, maybe the entire complex plane. So it's a kind of a stronger assumption, in my opinion, and but it's really necessary for this theorem. On the other side, on the other hand, the assumption, the geometric assumption that ensures the existence of rays is not important once you get away from your prejudice that escaping points have to be organized in nice curves. So when you drop the geometry, they're not organized in nice curves anymore, but you can find some topologically much more complicated objects which still morally act as the rays. And so this theorem can be generalized to these more complicated objects. You can completely drop the assumption that you have these geometric conditions, but things get very complicated, and so I'm not going to touch this today. Okay, so again, why do we care about the post-singular set being bounded? Because if the post-singular set, you can put it in a disk, then outside this disk, you can take open simply connected set, and you can take as many preimages as you want. And you can show, this is a modification of a classical argument, that your preimages, not only you have all of them and they're all univalent, but the diameters shrink. So if you take an unbounded, well, if you take the complement of the post-singular as a bounded set of singular values. So you remember we defined singular values. A priori, you could have like, well, I don't know if there are examples where every point in the complex plane is a singular value, but singular values may form an unbounded set. They may have non-empty interior. They may be a very complicated set. However, if you can put them all in one disk, there are lots of things that you can understand about the structure of the dynamical plane. Let me go back to an example that we all studied when we were, the pointer. So let me go back to an example that we all saw when we took our first courses in complex analysis. If you take the simplest possible transcendental map, which is just e to the z, the only singular value is 0, which is an asymptotic value and an omitted value. Because if you take a small neighborhood of 0 and you cut it out, the preimage of the complement is a right half plane. And so this right half plane maps all around this little disk that you can imagine you cut out. And what do you do when you want to define branches of the logarithm? You take a slit. Since the preimage of the complement of this small disk is in the right half plane, the standard slit that you take is the negative real axis. And now this helps you to define branches of the logarithms. Why? When you take the preimage of this curve, you get a lot of preimages, which are just straight lines, which look like this. And on each one of these half strips, each one of them maps one-to-one to the complement of this small disk minus the line. Okay? Now you have infinitely many singular values, non-empty interior, whatever you like, but you put it all in a disk, and you take a slit. So the pre-image of the complement of the disks, this disk, the yellow disk, is the one which contains all the singular values, and in our case, also the post-singular set. And you take the complement. The pre-images of the complement are these blue unbounded sets, which are called tracts, which map infinite to 1 to the complement of the disk. And you can take your slit delta. You have to prove that it exists, but this is not so hard. And this cuts your tracts into infinitely many fundamental domains. And each fundamental domain maps 1-to-1 to omega, which is the complement of the disk, minus this curve. What does it mean that it maps 1-to-1? It means that for every fundamental domain, I can define an inverse branch, which is univalent on this omega, on this complement of the disk minus delta. And another thing which is not hard to prove is that only finitely many of these fundamental domains can intersect the disk, essentially because pre-images of points cannot accumulate in any compact set. But anyway, so you really have to worry about the dynamics on these finitely many fundamental domains that will intersect the disk, because somehow, and this is a spoiler, but somehow when you have a fundamental domain which does not intersect the disk, it's like a map which maps completely out. So the inverse branch is mapping completely in, and then you have Schwarz's lemma, which tells you that you have an attracting point for the inverse map, that is, and that all the dynamics is going to be attracted to this point. So what do you do with this? You construct your sets with symbolic dynamics. Look at this. These fundamental domains give you a very natural partition of the set of escaping points. Why? Because if you're in escaping points, you can't keep and come back to this yellow disk. At some point, you need to be out forever. So at some point, it means that you will be in the fundamental domains forever. You will never be able to go back to delta again. So if you're in escaping points, you have a very well-defined itineraries with respect to this set of fundamental domains. So it's a natural way of defining symbolic dynamics on the set of escaping points. And this is what you can do. So this is a standard construction in dynamical systems as far as I understand. You want to put symbolic dynamics on some set, you do some partition of the plane, and then you look at itineraries of points, and you say that, and you divide your points into sets which have a prescribed itinerary. This is kind of what you want to do, but you can't do it exactly like this because you have some continuation of analytic branches. So you have to take pre-images. For example, you fix an itinerary, so the fundamental domains are countably many. So you can really imagine them to be integers, but it's kind of more dynamically meaningful to keep the notation in terms of fundamental domains. So you fix a sequence of fundamental domains. It's usually called an address. And you want to construct a curve of escaping points, which is labeled by this sequence, which will be your ray. How do you do this? Well, you start at some point, for example, at F2, and you pull back through the branch. You have to define the branches carefully, but you pull back inside F1, and then you pull back inside F0. And then you start at F3, you pull back inside F2, then inside F1, then inside F0, and so on. And you show that this process converges. So how do you believe that this process converges? Well, if your fundamental domains have a very nice geometry, for example, if they are rectangles, and they are mapped 1-to-1 in an affine way, it's very clear that when you do this process, you eventually get a line which is well inside your rectangles. But if they start having a weird geometry, and they start making gulfs going closer, and accumulating, the boundary accumulating over itself, and so on, then you will not get a curve. Okay, so this is where the geometric assumptions come into place. All this discussion just to give you an idea of how you construct these curves with symbolic dynamics, and let me tell you a bit more about this. So when you take a pullback of a fundamental domain which does not intersect the disk, then it's fully contained in the complement, right? So when I take the pullback of this, it will be fully contained inside the previous fundamental domains. And then I will do other stuff. I don't know what I do, but this pre-image of Fn-1 will be forever contained inside the previous domain. So, while if a fundamental domain does intersect the disk, when you pull it back, it will kind of stick out, and this fact of sticking out will kind of be preserved forever after. So if you have a sequence of fundamental domains and none of them intersect the disk, when you pull back, you get sets which are one inside the other. And in this case, it's kind of relatively easy to use some contraction argument to show that you do converge to a set, which if the geometry is nice, is a curve. And it's also easy to show that this curve, which will be the ray labeled by this sequence of fundamental domain, really has a one unique accumulation point. Again, because of this Schwarz lemma, which tells you essentially that all the component is mapped strictly inside itself, and then strictly inside itself again, and so on and so forth. You need to show that the contraction is uniform. But essentially, Schwarz lemma will tell you that in this case, you do land, and you land at a repelling periodic point. Mm-hmm. So there are two types of geometric assumptions that you need to do. One is to ensure that, so if this is your fundamental domain, it's very nice geometric assumption, but you could start having gulfs and subgulfs and some more gulfs, which they can go all the way there, but they can kind of not shrink enough, right? And this creates problems because the geometric lengths of this, the hyperbolic lengths of this curve can go to infinity, these curves can go to infinity, and this creates some kind of obstruction to the effect that when you pull back infinitely many times, you really get curves. And then there is another type of geometry.
How do you rule that out?
You don't rule that out, that's an assumption. When you construct the curves, this is part of the geometric assumptions that you need to ensure that your limit set is a curve. If you drop this assumption, you don't get curves.
The assumption is that doesn't happen somehow.
Yeah, the assumptions are complicated to write. Okay, there are two conditions.
So some analytic formulas that you can actually...
Yeah, there is a formula that you can check, and it works for all functions which are finite compositions of functions of finite order. So all functions of finite order are fine, and also all functions where you compose finitely many functions which are different between themselves, but all of finite order. That's a sufficient condition, but there are many more. And the other condition is at infinity. You need these fundamental domains. We imagine them to be like nice and straight. This is infinity. You need imagine your tracks to be like this, but this is not necessarily true. They could spiral around, okay? If they spiral more than a logarithmic spiral, it doesn't work. So these are the two geometric conditions that you need on the function. And they're both ensured once you take finite order or composition of functions of finite order. So this picture was just to convince you very philosophically that the problems that we have are all with fundamental domains which intersect the disk. With these pieces of fundamental, when we pull back, with these pieces of fundamental domains which intersect the disk. And there are many characterizations of landing. So the one that I gave you before is that a ray GS lands if and only if its closure minus the ray is just 1 point. But what usually people do, especially in polynomial dynamics, is take a fixed ray. So a ray which is mapped under itself by a function f, and of course periodic is the same. And you take a point here, and you start pulling back, okay? There is always exactly one branch which brings you back to the ray, and you look at how these inverse branches of this point behave, and you say that it lands if and only if the preimages along the correct branches of this point z converge to one single point, which I denoted by z naught. This is a very equivalent characterization of landing when you have a periodic ray. And then, here comes the question. Why do you need to take a point on the ray? Well, you don't. You take an arbitrary point. You take an arbitrary, you take an arbitrary point here, and provided you select the inverse branches that you have to be very careful about, for example, by taking some simply connected open set in the complement of the postsingular set, you have this shrinking lemma, which tells you that the preimages of this set will have diameter going to 0. So to check if a ray lands, it's not necessary to take a point on the ray of taking pullbacks. You can really just take any outside point in omega, in the complement of this disk, and pull back, and you know that the diameter of this thing will go to 0. So if the preimages of this point converge to one single point, also the preimages of this other arbitrary point will converge to a single point. And why do we care about this? Because we are not really able to work with the ray itself because it may have bad geometry. Like when you take exponential map, these rays are analytic curves. You can estimate the length of the segment of curves between a point and its image. They have a lot of nice properties. But the more your geometry goes bad, they may still stay curves, but they may become something like the Peano curves, which is known, I don't remember the name, but for which an arc connecting two points is infinite length. Okay, so they're much harder to deal with. On the other side, if you consider, if you realize that you can take an arbitrary point outside by the shrinking lemma, then you can choose your point in a place where you know how the images are going to behave. And there is a lot of delicate things to do with inverse branches, but you can do it. And you can define a special set which contains your base point that you have to choose very carefully. And you can choose your base set such that the preimages shrink to 0, and that it takes care of all these bad pieces of fundamental domains which were contained inside the disk. Moral of the story, to show if you take a ray and you want to see if it lands, then it's enough to check that the appropriate preimages of this special set V shrink to points. This is an auxiliary thing that you need for the proof. And this was the most technical thing. Now let me just tell you how you do it. This is not a proof. It's just the two things that you have to do. You have to do two things. Okay, what is the setup, okay? I'm trying to show you, so I'm trying to show that if you take a repelling periodic point, then you always find a curving escaping set with length there. This is very delicate. So you really need some kind of a priori bounds on this on some set which needs to shrink. And this is the delicate part, okay? And the strategy is as follows. You take your periodic point, which has some linearizing neighborhood, it doesn't matter which one, and you take the pre-image of this neighborhood inside itself. You know that it's strictly contained inside because the modulus of the multiplier is strictly bigger than 1. And there is a well-defined inverse branch which fixes this fixed point, and you need to do two things. The first one is to find a candidate address. Okay? You want to construct a ray which lands there. So you need to first understand which ray may have a good chance of landing there, and then to show that this ray actually does land there. And of course, I'm not giving you any details, but you really need to use, to construct a ray, you basically start with some approximation of rays that I am not going to talk about. But so the first thing you want to do is to find a certain number the first thing you want to do is finding a candidate address, and the second thing to do is you want to show that this ray with this candidate address actually lands there. And this is too technical, but here is kind of the idea of what you do. So you start with a certain, you can't work with the rays, okay? You need to work with approximations of the rays. So you find more or less a certain number of approximation of rays which intersect the neighborhood you choose, and you choose them so wisely that you kind of get a finite number of finite sequences that will kind of form building blocks of your address. And there is kind of a magical trick which ensures you that you get finitely many symbols and that you keep moving from finitely many symbols to finitely many symbols, so you really get a graph over finitely many symbols. This ensures you that you will get a path, an infinite path in this graph, which will give you a limiting address. And then you will have chosen the diameter, the pre-images of your auxiliary set V that we kind of discussed before, so wisely that you make sure they shrink fast enough to ensure that this candidate ray will land. Let me say you just a little bit more about these addresses. So what you really do is you fix a certain number of addresses, of symbols, chosen wisely, and then by pulling back under the map, which in the true map, the authentic map, which fixes your repelling fixed point under that branch, then you manage to to kind of form sequences of symbols which are longer and longer and longer. And this gives you, and of course, you need to make sure that you don't keep adding new symbols, right? Otherwise, this process is not converging. Imagine that instead of having f, you have numbers. If the first time your symbols are 0, 1, and 2, and the second step you are 0, 1, 2, and 3, and so on, and they keep increasing the number of symbols involved, then you're not able to find a convergent sequence and an infinite path, an infinite symbolic path. So believe me or not, I wouldn't believe it if I had listened to this talk, but it's true. You can find this path using this trick of managing to deal only with finitely many symbols, and then you can show that the ray actually lands there by using this abstract characterization of landing. And this proof does not only work for repelling periodic points, it also works for parabolic points, it also works for hyperbolic sets, that are sets which are expansive. They're kind of like a periodic point which doesn't quite come back to itself, but keeps moving around in a compact set, but the derivative is always strictly bigger than 1. This is basically a hyperbolic set, forward invariant compact set on which the modulus of the derivative is strictly bigger than 1. And it works without any geometric assumption, but then you need to get into topology and things get more complicated. So even though there is so much more to say, I'll stop here and thank you for listening.